Welcome to this movie on statistical mechanics. My name is Jos Thijssen and I teach statistical mechanics at the Delft University of Technology in the Netherlands. This is the third movie in a series of 3 on elementary polymer and solution physics. And in particular, this movie deals with polymers in solution, and the theory which describes those systems is the so-called Flory-Huggins theory. The first movie which I made dealt with free chains, where the chain doesn't have any interaction, the beads of the chain do not have any interaction. The second one was a movie on polymers where the beads cannot overlap, and then you get the so-called Flory exponents. You have a self-avoiding chain. And in this movie we are treating a much more complicated problem. Those are chains which cannot overlap, so the beads of the chains do not want to overlap. But in addition there is a solution present, and then you can envisage that either the polymers collapse into one part of the volume where they form a dense polymer melt, or they will really dissolve in the solution. And that's the problem I want to address in this movie, and I hope that you enjoy this movie and learn something about it on Flory-Huggins theory. In the Flory-Huggins theory for polymer solutions, we start with polymers whose beads cannot overlap. That's similar to the Flory mean field theory, where we had also beads that could not overlap. They had a hardcore repulsion and they were moving in the continuum space. Here we put the polymers on a lattice, and the solvent atoms of the solvent molecules are also put on lattice sites. And on each lattice site there can either be a polymer bead or there can be a solvent molecule. And we can envisage that in that case you have the following 2 situations. On the left hand side we see polymers. They are the colored sites. The color here only serves to distinguish the different chains. And we have also gray circles, white inside, and they are the solvent molecules. And we see that the solvent and the polymer, they mix, and so this is a real solution which is characterized by a high entropy. So we can say that here the entropy is high. It's certainly higher if we compare it to the right hand side, where we see that the phase has separated. So we have a region in space where the polymers all go, so they form a dense melt. And we have in addition a solvent which separates from the polymers, and so this is called the separated phase. The polymers here, they form a melt. And on the left hand side we have a solution. Although we can make a definite statement about the entropy, which is higher on the left hand case in the solution than on the right hand side in the separated phase, it's difficult to tell what the energy in the 2 cases will be, because that depends on how much the sites of the polymer, the beads of the polymers, like each other, and how much they like the solution, and also on how much the molecules inside the solution like each other. So we have interaction parameters that we will come back to in the end, describing these 3 different energies, so polymer-polymer, polymer-solvent, and solvent-solvent interactions. And depending on the values that these parameters have, the energy can be higher or lower on the right hand side than on the left hand side. The phase which dominates is the one which has the lowest free energy, and therefore we need indeed to evaluate the entropy for the 2 phases, and we need to evaluate the energy. And we start by the entropy. But before we do that, we need to define several quantities that we will use in the calculation. And the first one is n sites. N sites is just the number of sites in the system, so it's equivalent to the volume. The second number which is important is n, and n is the number of beads for each polymer. The next number is NP, and NP is the number of polymers we have in the solution or in the melt. So the number of polymer beads in the system is just N times Np. Finally, we have the number Q, and that's the lattice coordination number. That's the number of nearest neighbor sites for each sites on the lattice. So now we start calculating the entropy by imagining that we build up the system polymer for polymer, and we will use some mean field arguments in doing that. Before we continue, it should be pointed out that the grid that we have drawn here is a two-dimensional grid, but it could also be three-dimensional or one-dimensional or four-dimensional, whatever. We now evaluate how many possibilities we have when we build up the jth polymer of the system. So we assume that there are already j-1 polymers in the system. And we are going to build up now the jth polymer, and we start with the first site. For that first bead of the polymer, we can choose any site which is not yet occupied by the j-1 previous polymers. So in total we have how many sites at our disposal? We had n sites in total, and of these j-1 times the number of sites per polymer, and that was n, has been occupied by other polymers, by other beads, and therefore we have this many possibilities to put our first bead. For our second bead, we have, in principle, we can choose any of the Q neighbors of the previous one, but maybe that neighbor is already occupied by one of the previous polymers. So we have to multiply this by a probability that the site is unoccupied. And for this probability we use a mean field assumption. We just take Q times, then we just take the sites that are still unoccupied. So that's n sites minus j-1 times n minus 1, because we have already placed the first bead, and we have to divide that by n sites. This is a mean field assumption because we assume that the average probability of occupation is independent of the fact that we have placed a first bead here. So it's homogeneous everywhere in the lattice. That assumption is the mean field assumption. In order to see how many possibilities we have for the third bead, let us take first the first bead, and then we could put a second bead either here or there or there or there if you are on a square lattice. So suppose we have put it here. And then for the second bead, we can again, in principle, it has 4 neighbors, so Q is 4 in this case of a square lattice in the plane. But one has already been occupied, so instead of Q neighbors, we only have Q minus 1 neighbors where we can place the next site. And we should multiply again by this probability that that site is unoccupied. It could be that some other polymer, which started here, has occupied, for example, this or that site. And so what do we obtain? We have Q minus 1 times n sites minus j minus 1 times n, and now we have minus 2 because we have placed already the second bead, so there's one less site free. And we carry on in the same fashion. So For the kth beat, we have the same expression as for the third beat, very similar, except for the -2, which we had for the third beat. We have a -k plus 1 for the kth beat, and we carry on until we have exhausted all the n beats of polymer number J. All in all, for polymer J, in order to find the number of possibilities we have for building up that polymer, we should multiply all these numbers. So this number times that number, etc., etc. And we obtain the following expression. So recall that for the first site, we just had as many possibilities as there were empty sites. For the second one, we could take q neighbors, and then we should multiply that by the probability that they are unoccupied. That's this factor. Then for the next one, we have only q minus 1 because the previous beat was already occupied. And we have to multiply that by the unoccupied probability, p unoccupied. And we carry on like that until we arrive at beat number n. Now note that in the numerator we have a product of terms which decrease. So here we have a certain number. This is that same number, -1, -2, -3, etc. until we arrive at the last number. And there is a compact way of representing that, namely by the fraction of 2 factorials. And what we obtain then in the end is that we have n sides minus j minus 1 times n factorial. So that's what we would have if this would continue all the way down to 1. But that's not the case, so we have to divide out all the terms that are smaller than this. And that turns out to be n sides minus jn. So that takes care of all the integers in the denominator apart from q. Then we have one factor of q, and in addition we have n minus 2 factors of q minus 1. That's because we have the terms of q, they all correspond to links. If we have n sides, we have n minus 1 links. The first one of those is q, and so for the remaining n minus 2, we have q minus 1. And then we have this factor of n sides in the denominator. And that occurs for each beat, except for the first one. So that should be raised to the power n minus 1. So this is the number of configurations that we have for polymer number J. And in order to find the number of configurations for all the polymers, we need to multiply this quantity, omega j, for each polymer. So the j runs from 1 up to the number of polymers, and then of course we need to divide by np factorial, because when we reorder the polymers, then we have in fact the same configuration. In the end, it doesn't matter in which order we build up the polymers, and that's why we have to compensate here with the 1 over np factorial. So when we work that out, it's wise to start with a prefactor that's rather simple, because it's the same for each polymer, so we simply have to raise that to the power np. So we have first of all our 1 over np factorial, and then we have q to the power np, then we have q minus 1 raised to the power n minus 2 times np, and we divide by n sides. Raised to the power np times n minus 1. So the remaining terms are a bit more complicated. For polymer number 1, we have here n sides factorial, and we need to divide by n sides minus n factorial. So that's this expression for j is 1. So then we obtain the sequence of these terms, n sides factorial divided by n sides minus n factorial. And then we have the same term in the numerator and the new term in the denominator. That same term in the numerator, new term in the denominator, etc., etc. So we see that there are a lot of cancellations. This term cancels against this term cancels against that term, this term cancels against the next one, etc., etc. Finally, this term will also cancel, and the only terms which remain are n sides factorial, and this term n sides minus np times n factorial. So finally we have the same term as we had here, and then we are left with n sides factorial divided by n sides minus np times n factorial. And so that's the number of ways we can put the polymers in the solution phase. Recall that the solution phase was this phase that we had in the left picture. What we want to find out is whether the left or the right situation, so the solution or the separated phase, is stable. And we know that when we know the free energies of both, and we are dealing now with the entropy, which is an important part of that free energy. So for the entropies, we need to compare the entropy of this phase with that of this. And we have focused only on the entropy of the polymers, and in the right hand side we can use the procedure that we have followed here, except that we just assume that there is no solvent present and that we have fewer sites. So here are all the sites that can be occupied by polymers. It's just n times np, so that's the number of beads we have available in the polymers, and we have no solution. For the separated phase, that we use therefore the same expression, but now we take n sides to be equal to n times np. So for example, this term disappears then from the expression, and we then obtain 1 over np factorial, and then we have q np, q minus 1, n minus 2 np, and now in the denominator we have n times np raised to the power n p times n minus 1. And then we have, instead of n sides, n times np factorial. In order to find the entropy difference, we take the k log of the omega solvent minus that of the separated phase. And so that means that in the end we have to take the logarithm of the ratio of these two terms. And then one thing is simple. We see that these terms in both are exactly the same. And so we then recover the expression only with the different terms, and the result then becomes the following expression, which is rather cumbersome to work out. And in order to make life a bit easier, we define a new parameter, which is the polymer fraction. So we define a parameter that we call phi, and that is n times NP. NP is the number of polymers, N is the number of beads per polymer, so this is the total number of beads divided by the total number of sites, so that's the polymer fraction. And in terms of this parameter, we can express this entropy difference in a rather straightforward way. First, we recognized this parameter here in the first term in the logarithm, and working it out, we get np times n minus 1 times the logarithm of phi. And then we use the Stirling approximation for the other terms that occur here, all these factorials. Here is the result, where we have used the following. This is phi times n sites, and that directly gives rise to the last term here, n sites phi times ln n sites phi. Then we have here 1 minus phi times n sites, which gives rise to this term, and the term in the numerator is simple, it just gives me this. And then we realize that the last terms are all proportional to n sites, so we could put n sites here in the denominator. At first sight it seems that this term is not proportional to n sites, but np times n can be written as phi times n sites, and the minus np can be written as phi times n sites divided by n. And so we can then write the following for S. Delta S divided by the number of sites and divided by kb gives minus phi over n log phi minus 1 minus phi logarithm of 1 minus phi. This expression follows straightforwardly from the previous one. You just need to work out all the terms. One important remark: in working out the entropies for the solution and for the separated phase, I've neglected the multiplicity of the solvent itself, but that doesn't matter because that's the same in both cases, so that doesn't affect the final difference. The next step is then to calculate the energy, both of the solution and of the separated phase, and we start by the solution. Now the energy obviously depends on the interaction between solvent molecules, interactions between the polymer beads, interactions between polymer beads and the solution, and therefore we now introduce a few interaction parameters where we assume that there are only nearest neighbor interactions. And so for the solvent we have the parameter JSS, which describes as the solvent-solvent interaction, which only interacts between nearest neighbor sites, both occupied by solvent molecules. So we ask ourselves, how many such interactions will there be? Well, in total we have n sites, times q, because the lattice coordination number is q, so this is the total number of nearest neighbors, but we have counted them doubly, so we need to divide this by 2. We need to multiply by JSS, but now this is the total number of sites, and of course we can only allow sites which are not occupied by the polymer. And therefore, provided if we multiply now by the occupation probability that the first site is indeed not occupied by a polymer, we have 1 minus phi for that, because phi is the polymer fraction. And if we want the second site to be empty as well, we need to multiply once more by 1 minus phi, and therefore this is the interaction energy of the solvent. Then we need to take into account the solvent-polymer interactions, and we assume that the interaction constant we take for that, the symbol JSP. Now here is a section of a polymer, and it can interact with, in this case, two neighbors, because the other two have been occupied by neighboring polymer beads. And therefore we start by allowing each polymer bead to have neighbors, and there are n times np polymer beads. But because these two sites have already been occupied by other beads, we have here a q minus 2, because two sites have been occupied. And then we need to multiply by the probability that the remaining sites are unoccupied, and that probability is 1 minus phi. And then we multiply by J SP. Obviously, you could argue that we should also consider the first and the last bead, but we assume that we are in the large n limit, so we have long polymers, and then they give a negligible correction to this result. Next, we consider polymer-polymer interactions, and that's a case which is very similar to the previous one, except that we want the red cross sites now to be occupied by another polymer, by another bead. And it's important to emphasize here that with these polymer-polymer interaction, we do not include the interactions between beads that are neighboring on a chain. There are always the same number of neighbors on a chain, so that gives a constant contribution to the energy, and we don't consider that here. So we take the case where this site, the red cross, or that site is occupied by a bead of another polymer, or a bead further on this polymer. And therefore we have something similar to the previous one. We have n times np times q minus 1. But now we need to divide by 2, because we have both polymer sites. They are indistinguishable, so swapping them gives the same pair. And we do not want to overcount. And then we need to multiply by the probability that the neighboring site is indeed occupied, and that gives me a phi. And then I have a J polymer. And I can add up all these terms, but I've done something in addition. N times Np can be written as n sites times phi. And I've used that here. I have also used that for this contribution. And therefore, in the final expression, we have an extra factor of phi included in these two terms. And that enables us to write the solvent energy as n sites times a single energy. So we are interested in the end in the energy per site. We need to compare that solvent energy to the energy of the separated phase. And in that case, we have a fraction of the volume which is occupied by the polymer, and we have a solvent. And because the boundary is a lot smaller, it involves much fewer links than the bulky parts, we neglect the boundary altogether. So we consider the polymer volume separately from the solvent volume. Then we realize that every polymer in the melt has Q minus 2 neighbors, and we need to multiply this by the number of polymer sites, and that's n sites times phi. And for the solvent, we have n sites times 1 minus phi solvent sites. So we subtract the polymer fraction from the total. And then we have Q. Each site can have Q neighbors now, because there is no restriction. We are dealing with the solvent and not with the polymers. We need to divide by 2 for double counting, and we have a J solvent. In the end, we are interested in the difference between the free energies. So here we focus on the difference between these two energies. All the terms are proportional to n sites, so we can divide by that. And if we subtract these two expressions, then after some calculation we find the following expression. And we see that we have extracted now all the terms which depend on the polymer concentration in front of the square brackets. And inside the square brackets we have three terms, solvent, 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 polymer, and polymer, polymer. And we see that the terms where particles interact among particles among themselves, so with particles of the same kind, they have a minus sign, and for different particles we have a plus sign. Obviously it's this parameter just has a fixed value because the Q, the coordination number, is fixed, and all the interaction parameters, they depend on the chemistry of the solvent and of the polymer. So all these terms are fixed, and we lump all those terms together into KBT chi. That's called the Flory-Huggins parameter chi. And we see that although the original expression here does not depend on temperature at all, by this procedure we have introduced the temperature dependence in chi, such that for low temperature chi is big, and for high temperature chi is small. Now let us recall the difference in the entropy which we calculated before, and which is this expression, and that enables us to find the free energy difference. And using the delta E and using the delta S, we can find the delta F, just delta E minus T delta S, and then we have a lot of terms that we can work out. And the final result is then this expression that we see here, and this term arises from the energy difference. The other terms are just the delta S. And so this is the free energy difference between the solution and the separated phase. And this equation determines whether the solution is stable. That's the case when delta F is smaller than 0, because then the free energy of the solution is lower than that of the separated phase. And for positive values of delta F, we find that the separated phase is stable. Here you see a plot of delta F as a function of chi and of phi, the two parameters. The formula is given here on top. And the color indicates whether the value of delta F is positive. In that case, the separated phase is stable, or negative, that's the blue region, and then the solution is stable. And then in the right picture you see a few scans that were taken for fixed values of chi, so those are cuts in this direction. And you see that there are even values of phi for which the value for delta F can be either positive or negative depending on the concentration phi. In summary, we have compared two different phases for a collection of polymers and solvent molecules. The left phase is the phase in which the polymers mix with the solvent molecules, and so they form a solution. On the right hand side they form a separated phase. Which one of the two is stable depends on the relative free energies, and in order to calculate that difference we have first analyzed the entropy and then the energy, both in a mean field approach, and it turns out that these quantities can be expressed in terms of two parameters. The first of these is the polymer fraction, that's phi, and that's the number of polymer beads divided by the total number of sites. So we have NP times N polymer beads. NP is the number of polymers, and N is the length of a polymer measured in beads, and the remaining sites are occupied by the solvent. The second parameter is chi, that's the Flory-Huggins parameter, and it depends on the interaction constants. These are all nearest neighbor interaction constants. The first one for two sites, neighboring sites being occupied by solvent molecules, then solvent polymer, and then polymer polymer. The interactions where the occupations of two neighboring sites are the same, so that's SS or PP, they both have a negative minus sign, and the one in which a solvent talks to a polymer has a positive sign. Furthermore, there is some temperature introduced because we have divided by kBt. The stability of the phase is determined by the sign of delta F, which depends on those two parameters chi and phi. And here you see exactly for which values of chi and phi, the delta F, is positive, then it's red, or when it's negative, in that case it's blue.